Imagine if you could shrink down, like super small, and navigate inside the human body to fix things from within. Or maybe picture an invisible army cleaning up pollution right under our noses. It sounds totally like science fiction. Maybe like that old movie Fantastic Voyage, right? Or, like Richard Feynman talked about way back in '59, there's plenty of room at the bottom. But believe it or not, this stuff is actually becoming science fact. Today, we're doing a deep dive into this incredible, mostly unseen world of micro and nanorobots. And these aren't just like tiny wind-up toys. They're really groundbreaking tools that could potentially change everything. Medicine, cleaning up the environment, even manufacturing. So our mission today is to explore how these little marvels actually work, what they can do some amazing things apparently, and also what challenges are still out there before they become part of our regular lives. And helping us navigate all this is a really comprehensive technology roadmap review. It was published recently in ACS Nano 2025. It's called Technology Roadmap of Micro Nanorobots. And it's this huge collaborative effort, like over 70 researchers involved, big names like Joseph Wang from UC San Diego's Department of Chemical and Nanoengineering, and Martin Pumera from the Central European Institute of Technology over at Brno University of Technology. So this review gives us a pretty unparalleled look into this field. It's like our crystal ball for tiny tech. Okay, so technology this small. It makes you wonder, what are the really big problems these tiny tools are trying to solve? Why do we even need robots you literally can't see?
That's exactly the right question. I mean, think about the limits of the tools we have now, like getting a drug precisely to a tumor deep inside the body without hitting all the healthy stuff around it. That's hard. Or trying to clean up, say, micropollutants in water. You can barely see them, right? So these are microscopic problems, and they basically demand microscopic solutions. The whole point of this field is getting past the limitations of our bigger tools by working down at the scale of, like, cells and molecules. So it's kind of like sending in a miniature, really specialized surgical team. Or maybe an invisible cleanup crew that gets into all the little corners. That's a great way to picture it. All right, this next part is where it gets really, really interesting for me. How do these tiny things actually, move, get around? They don't have little propellers or engines we can see, do they? Well, not in the way we usually think of engines, no. But they have some incredibly clever ways to propel themselves. We can sort of group them into two main types. You've got your chemically propelled robots, think like tiny rockets using chemical reactions. And then there are the externally powered ones, which we control from the outside using things like magnetic fields or ultrasound, light, even electricity. Now, the chemical ones, the idea actually started a bit bigger and then got shrunk down. Way back in 2002, researchers like Whitesides showed centimeter-sized things moving themselves with platinum and hydrogen peroxide fuel. But the real breakthrough at the nanoscale came around 2004, 2005. That's when folks like Ayushman Sen and Thomas Malloch at Penn State and also Ozen's group up in Toronto, they introduced chemically powered nanorobots. We're talking really small, like 2 micrometer long nanowires, maybe platinum gold or nickel gold. And they just moved on their own in water with hydrogen peroxide fuel. That was a big deal, highlighted in that ACS Nano review.
Wow. So they're basically creating a little chemical reaction that pushes them.
Yeah.
Almost like a mini Alka-Seltzer tablet fizzing its way across a glass of water, but controlled.
Exactly. That's a great analogy. Often it's a process called self-electrophoresis. The chemical reaction makes a little electrical field that pushes the robot. Or sometimes, it's literally bubbles. Bubble propulsion.
Yeah.
Like a tiny jet spitting out gas.
That's pretty clever. But okay, the external power stuff. I mean, imagine steering something inside your eye using a magnet on the outside. That sounds like magic.
Right. And magnetic propulsion is actually one of the most precise ways we have to do that remote control. A really key example here is from Ambarish Ghosh and Pierre Fisher. They were at the Roland Institute at Harvard back in 2007. They used this cool technique, glancing angle deposition. You can sort of think of it like spray painting at an angle to build up shapes, to make billions of tiny helical nanopropellers, like little corkscrews, super small, maybe 200, 300 nanometers wide, couple micrometers long, made of silicon dioxide with a magnetic bit. They even got a U.S. patent for it. And what's really neat is around the same time, other researchers at Roland, like Howard Berg and Linda Stern, they were studying how actual bacteria swim using similar corkscrew tails, their flagella. It's a great example of looking to nature.
Billions of microscopic corkscrews. That number is just staggering. And they move just by spinning them with a magnetic field, like a tiny drill.
Precisely. You apply a rotating magnetic field, it creates torque, spins the helix, and it drills through the fluid. Simple as that, conceptually. But magnets aren't the only game in town. Sound waves are another big one. Daniel Ahmed and his team at ETH Zurich, they've shown how acoustic streaming, basically using sound waves to create tiny fluid flows, can push these robots around. And others, like TQ and colleagues writing in Applied Physics Letters back in 2016, developed tiny resonant cavities. Sound makes them vibrate and spin things. And just recently, a 2024 preprint from Shi and others described a stingraybot using, get this, over 10,000 tiny resonant bubbles to make it undulate, swim like a real stingray. Oh, and we shouldn't forget electric fields. Orlin Valev's group at NC State back in 2006 and ACS Nano showed that tiny semiconductor diode particles could propel themselves in water using electroosmosis. So using electricity to interact with the fluid. Okay, now here's something really fundamental you need to grasp about movement at this scale. It's weird down there. Fluids behave very differently when you're that small. Inertia, the tendency to keep moving, like lighting it, basically disappears. Instead, viscosity, like stickiness, totally dominates. This is what E.M. Purcell famously called the scallop theorem back in 1977. He pointed out that if you just do a simple back and forth motion like a scallop opening and closing its shell, you won't actually go anywhere in these conditions. You just wiggle in place. It's called a low Reynolds number environment.
So what does that mean practically? They can't just, like, flap wings back and forth. They need a trickier way to move, like wiggling or corkscrewing, something that isn't symmetrical.
Exactly right. They need what's called non-reciprocal motion, something that breaks that symmetry. That's why you see so many designs that mimic nature helical screws, like bacterial flagella, or undulating motions like how sperm swim. They figured out how to beat the scallop theorem billions of years ago.
It's amazing what these single robots can potentially do. But what about teamwork? Do they, like, form swarms? And are they getting smarter? Can they think?
Yeah, absolutely. Both swarms and intelligence are huge areas. Many tasks are just too big or complex for one tiny robot, so researchers are developing microswarms that can work together, kind of like a school of fish or a flock of birds, right? They can be controlled collectively using those same external fields, magnetic, acoustic, electric, light, or even respond to chemical signals as a group. An intelligence that's pushing towards what's called embodied intelligence. It's about integrating some sensing and processing right onto the robot, maybe combined with remote control using AI and machine learning, the off-board brain. For instance, Han and colleagues showed semiconductor circuits that move with AC electric fields, but add a magnetic patch, and you can steer them. And the ACS Nano roadmap mentions using machine learning techniques like Q-learning or deep reinforcement learning to actually train these robots to navigate complex paths, basically teaching them to find their way.
Whoa, tiny robots that can sense, react, and even learn. That's really mind-bending stuff. And you mentioned some are inspired by biology or some actually using biology.
Indeed. The field of biohybrid microrobots is fascinating. Back in 2013, Mariana Medina Sanchez, who was at CIC Nanobiani BRTA then, and her team did something amazing. They used actual living sperm cells to power microrobots. They basically designed tiny magnetic microtubes that could capture a single sperm cell by the head, and then they used magnetic fields to steer the whole sperm-robot hybrid. And even earlier, in 2007, Bashir and his colleagues reported one of the first biohybrids using Listeria bacteria. They got the bacteria to carry nanoparticles for gene delivery. It's this incredible merging of living cells and engineered materials.
Okay, this is all incredibly cool, but let's bring it back to, us, the listeners. Where could these micro and nanorobots actually make a difference in our lives, and, like, how soon?
Right, the real-world impact. Well, the potential is just huge. Biomedicine is probably the front runner for major impact, especially targeted drug delivery. Think about a robotic pill. This isn't just fantasy. In 2018, Joseph Wang's group at UCSD actually demonstrated this. They put drug-loaded micro-robots, these little Janus spheres made of magnesium, inside a standard pill capsule. When the pill dissolved in the stomach, they even showed this in pigs, the microrobots were released, propelled themselves around, and significantly boosted the drug's absorption. That was in ACS Nano.
So they can actually get inside, move around, and deliver their payload right where it's needed.
Yeah.
With that kind of precision.
That's the goal, and they're making real progress. Wang's group, this time affiliated with Caltech, showed tiny tubular robots made of pitocin that could swim effectively even in the thick mucus lining of a mouse stomach. And then Esteban Fernandez de Avila and colleagues reported the first actual therapeutic use in vivo. They use microrobots to treat a bacterial infection in the stomachs of mice. That's a major step. And here's a real wow fact, also from Esteban Fernandez and team in ACS Nano in 2017. They loaded nanorobots with a protein called caspase 3. When they triggered these robots with ultrasound, they induced apoptosis, that's programmed cell death, in up to 80% of human stomach cancer cells. And they did it in just 5 minutes. Imagine that speed and targeting. And remember those sperm bots? Mariana Medina Sanchez, later in Dresden, took that idea further. They loaded human sperm with an anti-cancer drug, doxorubicin. They then guided these drug-carrying sperm inside tiny 3D printed structures, directing them right into lab-grown spheroids of patient-derived ovarian cancer for targeted treatment, and getting into tricky tissues. Pierre Fish's team in Nature Communications in 2011 showed magnetic microhelices could actually penetrate the vitreous humor of the eye, that thick, gel-like stuff. They coated the robots with a sort of super lubricant layer to minimize damage, crucial for working in delicate places like the eye. But it's not just medicine. These robots have huge potential for cleaning up our environment too. People are developing them for water purification, getting them to grab onto pollutants or break them down. Song Song Tang's group at Caltech, writing in ACS Nano in 2021, created these really neat biotemplated tubular microrobots specifically for cleaning soil. They integrated different functional nanoparticles onto them, iron oxide, manganese dioxide, stuff like that. And these little guys could degrade a whole range of nasty pollutants, antibiotics, PAHs with really high efficiency, like 80 to nearly 100% in just 15 minutes. Think about deploying those in contaminated sites. And they're great for sensing, too, detecting things at really low concentrations. For example, a 2021 ACS Nano study showed they could use the motion of microrobots to detect glutathione, which is a biomarker for various diseases. And the cool part, they track the speed changes using a simple 3D printed device attached to a mobile phone with a cheap lens. Very clever. The review also mentions work by Wang's group on using them to decontaminate chemical warfare agents and others using them for food safety, like detecting toxins or bacteria.
Okay, this sounds like the future is arriving incredibly fast. But if these robots are so powerful, why aren't we seeing them everywhere already? What's holding them back from, widespread use?
Yes, the reality check. That's the multi-million-dollar question, isn't it? There are definitely some significant hurdles still. First, especially for anything going inside the body, is biocompatibility and toxicity. Are the materials safe? Will they break down harmlessly? Or will they cause problems? Ideally, you want materials that are biodegradable and clear out after doing their job. Getting new materials approved as safe, like meeting the FDA's generally recognized as safe or GRAS standard, takes a lot of testing. Then there's lifespan and stability. How long can these tiny machines actually function in complex, messy environments like the bloodstream or soil before they just, break down or stop working? Tied to that is manufacturing and scale up. Making a few in the lab is one thing. Making billions or trillions of them consistently and cheaply, that's a massive engineering challenge. We mentioned Ghosh and Fisher making billions of nanopropellers, which was great for labs, but full industrial scale is another beast. Though the ACS Nano Review does point to promising new methods, like electrospinning used by Juzia Cruz Group at Fudan University. That might offer cheaper ways to make lots of nanofibers and tubes, simplifying production. Control and navigation are still really, really hard too. Think about trying to steer something precisely through flowing blood or dense tissue. It's incredibly difficult. And our imaging tools have trade-offs. Optics give great detail but can't see deep. Ultrasound sees deeper but is blurrier. So tracking them perfectly is tough. And of course, regulatory frameworks. Like any powerful new tech, we need clear rules. Rules for safety, handling, data privacy if they collect information, ethical use, even environmental impact, the whole ESG picture. Public trust depends on having solid regulations in place. Plus, believe it or not, we still don't fully understand the exact physics behind some of the basic propulsion mechanisms, like how those platinum bots work in peroxide. And if you don't fully understand it, it's harder to optimize it.
Wow. Okay, so there's still quite a bit of fundamental science and heavy engineering needed before these tiny titans are really out there saving the day routinely. It's way more than just making them small.
Exactly. Safety, reliability, cost-effective mass production, precise control, clear rules. It's a complex path from the lab bench to your local clinic or environment, but the progress we've seen already is just phenomenal, truly inspiring.
All right, so as we wrap up this deep dive into the micro and nanorobot world, let's hit the key takeaways. First, these tiny machines are definitely moving from sci-fi to reality. They use all sorts of clever ways to move chemical reactions, magnets, sound, light, electricity, often inspired by nature itself. Second, the potential impact is enormous. We're talking about super precise drug delivery inside the body, new ways to clean up pollution in our water and soil, and incredibly sensitive diagnostic tools. And third, despite the amazing potential, getting them into widespread use means tackling some big challenges. making sure they're safe and non-toxic, figuring out how to make trillions of them reliably, controlling them perfectly in complex spaces, and setting up clear rules for their use. I think the big picture idea here is that this tiny technology could really change how we tackle some of our biggest problems, giving us precision and access we just never had before. So here's something to chew on. Thinking about all this potential, what previously impossible task do you think these tiny trailblazers will conquer next? And, maybe just as important, what ethical guidelines do we need to put in place as they get closer and closer to being part of our everyday world?